Hi, this is Sholey Physics, doing an episode on applying Coulombs Law. I'm using a worksheet called May the Electric Force Be With You that I use with some of my students. So just transition here to our page. You can print this out. I'm going to put a link to it in the comments and information down below. So we got Charles Coulomb formulated this expression. Got Kc is the Coulomb constant, Q1, Q2 divided by R squared, and all that equals an electric force. So wait, hold on a second here. What is all this? So we have an expression here relating the strength of an electric force between two charges to the amount of charge of each of those two charges, which is the Q, the R, which is a distance between them, and some kind of experimentally determined constant. So that's a lot of stuff just to throw at you here, but in essence what this is a plug and chug kind of expression. There's a couple of goals here that I have to instruct you on. First off, we're applying some skills that you learn in algebra. You take a couple of numbers, what is Q equal to, what is R, what is K, you plug them in and you solve for F. But another goal is that in physics we've got these variables that often are the same letter. So in algebra, X and X, they're the same thing. You can't put two X's in one expression and have them mean something different. So what we're dealing with here are the same quantities but different sources. So Q1 and Q2 are labeled with a subscript to show that they're the same physical quantity of charge, but they're from two different particles, two different objects. They could be like a proton and an electron, or two protons even. Or it could be a couple of different spheres that are large sizes, not just this miniature little atom. There's Kc, which K is often a letter used in physics as a constant. So with the little subscript of C on there, this indicates a Coulomb constant. And then we have R, this isn't R2, this is R squared. Okay, so any numbers that you see above in the subscript area are mathematical expressions, but any subscripts, think like a subway is beneath the pavement, not a Subway sandwich, but the subway train. It is beneath the line of this writing here. So Q and a subscript of 2 would indicate the second charge, okay, or second object with a charge. So these are subscripts and they just describe what the variable is. Okay. So we've got Kc, Q1, Q2 over R squared. What's this showing us first off? Well, it's showing us is if we increase the amount of charge between charge 1 or charge 2, what's that going to do to the force over here? It's going to increase the force also. So if we double one of these Q's, we're going to double the force, okay? What else can it show us? If we increase the distance, how's that going to change? Well, if we increase the number in the denominator, what's going to happen to the force? It's going to get weaker. So if you take a number divided by 2 or divided by 3 or divided by 4, it becomes 1/2, 1/3, 1/4. And every time you increase that denominator number, you decrease the value of the force. But this isn't just a inverse relationship, it's an inverse square. And you might go back and see that inverse square law video that I produce on actually measuring the magnetic field strength of a magnet. So hopefully that'll come in there. So that's where that inverse square law comes in for distance. And finally we get to this Coulomb constant. When Charles Coulomb measured, got some evidence for his expression, actually formulated this. There's an excellent experiment you can look up on him. So that experiment helps determine for the first time this Coulomb constant. It's just a number, just like pi. It is always 8.99 times 10 to the 9th power. I like to shorten that 9 times 10 to the 9th power. Okay, if you plug in a 9 times 10 to the 9 in these expressions, and when we're solving for problem 1, 2, and 3, you're not going to get a significantly different answer if you use 9 instead of 8.99. All right. So there's one little last thing I like to talk about here is depending on your math level, you may or may not be comfortable with the look of this expression here, but Kc multiplied by the quantity of all this is the same as taking a force equals Kc, and putting that up there with the Q1 and Q2 in the numerator. Okay, so just like if you take 2 times 1 or 1 times 2, you get the same result out of it. It doesn't matter if you multiply it on top with the rest of the Q1 and Q2s, or multiply it after you determine the quantity, Q1, Q2 over R squared. So I usually write it more like this instead of how I have it here in this expression. But all those different ways are very valid. Okay, so I've got some information given here below. We're not going to forget that Kc is 8.99 times 10 to the 9th power. You'll see that this makes it a very significant force. You don't have to have much charge at all, relatively, to make a significant force. In fact, you can rub a balloon on your shirt, build up some static electricity, and put it onto a ceiling, and through some neat phenomena not mentioned in this video any further, that balloon will stick to the ceiling. So this just a little bit of static charge can overcome the weight of that balloon. That's a fairly significant force. So that's what this is showing here. This measured Coulomb constant is a large number. Now the rest of these units, depending on your level of physics and what, for whatever reason you're watching this video, you may need to use these units if your instructor needs you to. But for the time being in this video, I'm not going to be including the units in this discussion. All right, Q. So a reminder what Q is. Q is in units of coulombs. All right, that's the SI unit for charge, electric charge. And R is a radial distance. I should say a radial vector because it has a direction to it. It's in units of meters. Now, radial is the direction. It means along the radius. So think of a circle. Any direction that goes outward from the center is a radial direction. So what this is saying is if we've got a charged particle and we put another charged particle near it, it doesn't matter where we put that second charged particle, as long as it's its distance r, it's going to be the same strength of a force. Now if we double r, it's not going to be the same because r is greater. But let's say the r is 10 centimeters. The radius is 10 centimeters to the left of that first charge, or above, or to the right, or below. The strength of the force will be all the same at those locations. All right, and this final note here, the charge on an electron this is called the elementary charge, 1.6 times 10 to the negative 19 coulombs, and because it's an electron, it's a negative value there. Now I made a bunch of scribbles just trying to highlight, but an electron has a negative 1.6 times 10 to the negative 19 coulombs, and a proton has a positive same amount. All right, that seems to come, as far as we can understand about quarks, from the combination of quarks that make up the proton and the electron quark itself has a negative charge of the same amount. Investigating the weak nuclear force, a neutron can decay spontaneously into a proton and an electron. That's where we get radiation from. A lot of forms of radiation. But anyway, coming back to it, those two charges have to be exactly the same amount, or else law of conservation of charge falls all apart. Anyhow, that's another time. So we are ready to use this expression, and we're going to do problem 1 here together. So if you've got your paper, you can go ahead and work with me here on number 1, and I'll get you started on number 2 in this video, and I'll leave you to finish number 2 and complete number 3 on your own. So an electron and a proton are a distance 5.3 times 10 to the negative 11 meters apart. Draw a force diagram showing the force the electron feels from the proton. So if you haven't drawn a force diagram before, it's fairly easy. What I'm going to do is just indicate a proton with a positive, an electron with a negative, and we need to draw a force vector, an arrow, showing the force the electron feels from the proton. I'm using some touchy-feely language there, okay? Feels from the proton. So is it going to feel an attracting force toward the proton or a repelling force away? If you at least work with magnets, you'll know the north and south poles attract. So opposite poles attract one another. So These are two monopoles, so a positive and a negative charge will attract. That means this negative electron will be forced directly to the left. So we have a direction for that electric force. There's a subscript Fe. Okay. Now, we got the direction. It's going to attract. Well, what else do we need to find? The magnitude. Now that's the amount, and that's where this equation comes in. Find the magnitude of the electric force between the two, between the electron and the proton. So here's a charge, Q, and here's another charge, Q. Now this is an electron, the charge of an electron, and this is a charge of the proton, QP. Here we have a distance. They're this far apart. What is that? Well, if we have the distance away, this proton is applying a force to the electron, and the electron's applying an equal and opposite force to the proton. How far apart are they? Well, if this is the proton there, and if we're to measure this distance, that will be a radial distance. If you can imagine a circle around that proton, it's a very bad orbit there. But if the electron dances around the proton in a circular orbit, it remains at the same distance, r. And this is the approximate distance or size of a hydrogen atom. 5.3 times 10 to the negative 11 meters. If any of you have taken chemistry, you might have learned of the angstrom. 10 to the negative 10 is the approximate size of many atoms. So that's just a little bit bigger than this. This is about half an angstrom here. Anyhow, back to it. What we're going to do is write down the equation we're going to use. Electric force equals Kc Q1. Now in this case, I'll go ahead and put a QP, the proton, and the second charge is QE, the electron. So you can change those subscripts anytime you want to be as descriptive as possible. Then we have R, the distance between them. So is that it? Are we ready to go? Wait a second. What did I leave out? The squared. This is an inverse square law. So as we separate those charges, the force should decrease according to that inverse square law, that R squared. So write it out, and now we're going to plug in. What is the force going to equal? I like circling things just to make sure we all know what we're talking about here. Equals Kc. Now remember, Kc is like pi. It's a constant, like 3.1415926. I guess that's it. So that is pi, but this one's not pi. This is the Coulomb constant. So we're going to insert our Coulomb constant value, 8.99. You know what? I'm going to go out on a little limb here. Just going to say 9 times 10 to the 9th power. Not 9 times 10, not 9 times 9. 9 times 10 to the 9th power. Just shortening that a little bit. If you want to get real formal, use that 8.99 because that is the more accepted value there. And now, charge of a proton. Oh, the problem doesn't say anything about a proton. Sometimes you got to look it up. And remember, we've got a reference up here. Whenever we're dealing with protons, we're going to use a positive 1.6 times 10 to the negative 19 coulombs. So it actually takes a lot of protons, a lot of unpaired protons or a lot of unpaired electrons to make 1 coulomb of charge. We'd be talking about a lot of force if you took 1 coulomb of charge and bring it 1 meter away from 1 coulomb of charge. We're talking about 9 billion newtons of force, and divide that by about 4.5 to get pounds, and we're still talking about a lot of force here. That'd be about 2 billion pounds of force between those two. So just a tiny proton or tiny electron in itself, well, we should have a tiny amount of force here, but relative to one another, it is still huge. We're talking about a little tiny electron orbiting at near the speed of light around this proton. And that's just an incredible speed to keep moving around. So this has to be a significant force on the electron to keep it attracting towards the proton and not leave it, if we look at it in a Newtonian kind of a way. Now we're going to take all that, Kc Q1 times Q2 divided by R squared. And our distance is 5.3 times 10 to the negative 11. All right, is that it? Oh, wait a second. I made that mistake on purpose again. Because oftentimes my students, when doing this, their eyeball is going to catch this this exponent of -11 up here and forget to square it. So yes, we have to square that. Which brings me to another reason why I'm doing this with you all, is I want to show you the power of your calculator. You do not want to be using a wimpy little calculator from your phone. You want to use something that's souped up a little bit. Not even one of those like cheap $3 calculators. You need at least a scientific calculator, and if it's a graphing calculator or something like a TI-30X2S, it's a great like $12 calculator that gets the job done really well. So I recommend getting one of those calculators. But we need to calculate these really small and really big numbers and throw them all together here, and be very careful how we punch in our numbers. So here's my calculator, and we're going to go ahead and plug these in. Now there's a couple ways to do this. You can do it the long way, and I'm going to do the long way first. But the long way, sometimes you make a few mistakes, and I'll show you why. So anyway, you can start out like 9 times 10, and we're going to use this little character on your calculator. May look a little bit different, but mine's a little caret. So right above the division sign, I'm going to hit that button. Okay, so that's power of 9. All right, I have to move, use that little arrow over to get off of that. And I'll multiply that by 1.6. I'm going to leave off the 0 times 10 to the -19. Now be careful here. If you get an error out of yours, you may have plugged in the minus sign instead of the negative. So if you look next to the enter key, I'm going to hit that little negative sign. And you don't want to hit the minus sign under the multiplication key and above the addition key. It's to the left of that enter sign and below the number 3. So that's a -19. You hit the right arrow again to get off of that. And we're going to multiply that by the charge of an electron. Again, negative. We want to use negative instead of minus. -1.6 times 10 to the power of -19. All right, so that's the top line. Don't hit enter here. All right, we want to make this one line, because if we make a little mistake, there's a way to go back and change it easily. But if you keep on hitting enter, it makes it a lot harder to go back and redo your plugin. So go to the right. Now, the first way I'm going to solve it, listen carefully, I'm going to solve this incorrectly first, because a lot of students might make this mistake. So don't make this mistake. We got to remember order of operations here. This calculator knows the order of operations. So when it sees multiply and divide and exponents, it's going to do exponents first before it multiplies and divides. See, under here we've got a 5.3 times 10 to the -2 right in here. Okay, so right in there, 5.3 times 10 to the -11 to this quantity squared. So we want to make sure we get all of that in there. So if you plug that in without the parentheses, you're going to get a problem here. So if I just say divided by 5.3 times 10 to the power of -11, and then I square that, my calculator's kind of formatted it for me to give my eyeball a clue that I didn't do this quite right. But if I hit enter, I get a really strange looking answer. -4.3 yada yada e -150. Now when I talk about this little calculator language, the little e stands for times 10 to the power of. This is scientific notation here. So 4 times 10 to the -150 means a number that has a decimal and then 0.00000 150 times before you get to 4. I think that's, we're looking for a small number here, but not that small. So what this incorrect calculation has done is it has squared the -11 power first before doing all the rest. So we want to make sure we divide by this quantity, 5.3 times 10 to the -11 quantity squared. You got to do that first before all the other multiplication. So this is where I was saying with your calculator, if you make a small mistake, like you need to change a negative to a positive, or you accidentally did a minus sign instead of a negative, like I mentioned earlier, hit second enter. Or on your calculator, you might just be able to push up that top arrow to go back up into the equation you just edited. And look, I don't have to do much to change it. I can say, oh, I kind of messed up on that part. I'm going to delete the 2 and close a I gotta get off that exponent part there. I need to close the parenthesis and square it. And I also have to put a parenthesis in the front of this. These are called fat fingers. I pushed something I didn't mean to. So that was a 5-point hit. Second insert. A lot of crazy things can happen here. All right. Insert a parenthesis. There we go. So we have divided by quantity 5.3 times 10 to the negative 11 squared. And that is the value we're looking for. Okay, so we can add that up here. Negative 8.2 times 10 to the negative 8. Now all your answers need units. So what is the unit for force? In America, you might use pounds, but we're using the international system, SI units, or SI, and that's newtons. All right, there's about 4.445 newtons in a pound. I'm just going to check over my work here, make sure I plugged in everything correctly, and I think I did. So that should be the answer you come up with. If you've got anything different, go back through this video, see if you plugged it in the same exact way. Now there's a couple different ways to do this. This was kind of a long one, and if you forget parentheses, you might mess up a little bit, especially if you're dividing. So I want to show you one more way. It's actually a little bit shorter. There's less key presses, and you have less need of using parentheses. All right, so I'm going to plug in the same thing with a different way, but what I'm going to use, I'm going to plug in that 9 first, but instead of times 10 to the power of, I'm going to use a little key here. It's calculator language. If you look at my calculator, right above the number 7 is the comma, and in gold lettering says EE. What I'd like you to do is find your EE on your TI calculator if you've got a TI. All right, this is calculator language, and what is going to happen when you hit second, comma, you're going to get an E showing up. Now if you have a different calculator, it might actually put in times 10 to the power of type of thing in there, but that's calculator language for times 10 to the power of. Now I don't put in 10, I don't put in exponent here, I don't put in multiply, I just put in 9. Now this isn't the first 9, this is our, right here, we've got 9 times 10 to the 9th power. So the second 9 I put in is after that 10. And now we're going to multiply that by 1.6 e negative 19. So notice I didn't put in the times, the 10 to the power of, just 1.6 e negative 19. That's it. You'll notice already it's a little bit shorter. There's less key presses. I don't have to push the arrows to move around to get in the right place. I'm going to do a negative 1.6 e negative 19. And here's the neat part. When a calculator sees 5.3 e negative 11, it thinks that's all one number. So you actually don't need to put the parentheses on this one. The order of operations will do the exponent first and consider that 5.3 e negative 11 to be one single number that you don't have to do multiple operations on. And we're just going to square that. And when I hit enter, you'll notice I get the same exact correct answer out of it. A lot less key presses, it's not going off the screen, and it's a lot easier to plug in. Problem number 2 says 3-point charges are in a line where Q1 is given, this is a different amount of charge. So we don't need to use the proton and electron anymore. This is charge 1, negative 5 times 10 to the negative 9 coulombs. Q2 is negative 2 times 10 to the negative 9 coulombs, and Q3 is 6 times 10 to the negative 9. So take a note of that this is a positive 6 there. Find the magnitude and direction of the resulting force on Q2. So we're really looking at this middle charge here. What's going on with the middle charge? So first what we're going to do is consider charge 1 and charge 2. We're going to find the force between 1 and 2. Okay? And I'm going to set that one up for you. But then you're going to have to find the force between 2 and 3. All right? Because there's two things. There's two objects now acting on that middle one. This is kind of like, let's say Mars. The planet Mars has two moons, Phobos and Deimos. And there's two small kind of rocks looking things, tiny rocks. They don't look like really big moons like our own moon. All right? But it's like Mars is in the middle, and Mars is Q2, and Phobos is Q1, and Deimos is Q3. And they're kind of both pulling on Mars, and Mars is pulling on them. So there are two forces between 1 and 2, and between 2 and 3. Okay, and you don't put all the charges together. This doesn't turn into Q1, Q2, Q3. This is only the electric force between two charges. So we're going to add them up separately here. So we're going to take a KC, charge 1, charge 2, that's 2 there, divided by distance squared. So what distance should we use over here? This would be the distance between 1 and 2. Whoa, what is that? That's just some funky, some crazy subscripts there. But this just says the distance, the r, between 1 and 2 squared. Okay, so plugging in, we're going to have a 9 times 10 to the 9th power. By the way, when you're writing down your numbers, I might have just sent you on some kind of mathematical calculator high going, oh, I can use E now instead, right? Well, still when we communicate to other people, we say times 10 to the 9th power because we don't always have the context of a calculator to throw at people. Some people may have never used that. So if they just see you write 9E9, they're going to like, what is that? That's not math. So write 9 times 10 to the 9th power. Charge 1 will be -5 times 10 to the -9 coulombs. Make sure yours is a little clearer than mine. And charge 2 is -2 times 10 to the -9. Divided by what? R. What's the R between Q1 and Q2? It's 3 meters. So we're just going to plug in a 3 here. 3 squared. Okay. And that's where we're going to leave you. What I'd like you to do is really think about what the total force on Q2 is and Q3 is going to be. No, sorry. But the total force from Q1 and Q3 are going to be on Q2. Should you add them? Should you subtract them? That's something you might want to talk about with your instructor. But I'm going to leave that one up to you to solve this, calculate it out, and then figure out what you're going to plug in here for Q2 and Q3. And somehow you're going to add those together to find the total force. And finally, after that, there's a nice little urban myth. If you touch somebody, poke them in the arm, are you really touching them? Well, it's all kind of how you mean touch. But if you're talking about a proton coming into contact with another proton, can that happen? That's what you're going to find out in problem 3. So I hope it's been a little bit long, but I hope it's been helpful to work you through this worksheet.